Hello, and welcome to the first lesson of CS 6120 for fall of 2020. I am super excited for the semester, and I'm excited to get our hands dirty with a bunch of gnarly compiler implementation stuff. To get things started, I wanted to have a brief conversation, an asynchronous discussion, about why we bother studying compilers. And I think that it's really easy to get the impression that the reason for studying compilers, for doing research on compilers and for building compilers, is to make programs go faster. That's what your compiler does. It sort of takes, that's what we can sort of see most visibly in how compilers get better over time. That is that you take the same code, you compile it with a better compiler, and it generates faster code. And this is indeed one of the big classic areas within compilers. Compiler optimization is a big important topic that we're going to be spending lots of time on in this class. However, I wanted to emphasize that just making programs go faster is just one tiny thing that we do within research and compilers. And that this class is going to be about the much broader set of topics that you might call language implementation. That is, doing what it takes to take a programming language out of the theoretical realm of the human's mind and turn it into code that can actually execute one way or the other. And yes, it's important that code goes fast. It's important that it be efficient, but there's many, many other things that go into making a compiler. That is that are parts of implementing programming languages. So if you can, right now I'd like you to pause this lecture and think a little bit more about what goes into the implementation of a programming language other than just compiler optimizations. And if you say parsing, you are immediately kicked out of this class. That's just a joke. But this class is not going to be about parsing programs. That is a part of lots of compilers courses out there, but the course is going to be about the sort of the deeper topics of the semantics of programs. So not just thinking about the syntax, but how we implement the kind of the meat of what programs actually mean. So you can pause this video here and answer this question in the discussion topic associated with this lesson. Did you know that lessons in 6120 this semester come with discussion topics? They do. Let me show you how to get there. The way you get there is you go to the 6120 website, and there's a tab up at the top called Lessons. So far, there's only one lesson, the one that you're watching right now. But for a given lesson, there's a discussion link, which takes you to a topic within our Zulip space. And this is where you can respond to things that are directly about this video or anything else within this lesson unit. I'd like you to respond now with just brainstorming what goes into the implementation of a programming language. To get things started, I have one idea, which is that some language implementations do a lot of checking at runtime to enforce invariance. That is to rule out common classes of errors by checking for them and throwing exceptions at runtime. Dealing with all those exceptions is part of the implementation of a language. And it's something that we will consider as part of the broad topic of language implementation in this class. So think of one of these things, and please post it in the associated discussion thread. Thanks for all the great ideas that you've just posted to the Zulip topic. I wanted to spend a little bit more time thinking about the optimization question. Associated with every lesson in 6120 is some optional reading that you can do ahead of time. You probably didn't do this reading because it's the first day of class, and I didn't even tell you to look for reading to do it associated with every lesson, but we can look over a little bit now. It's just a really small paper that I think you might get a kick out of. So on the page for a given lesson, there are some links at the top to optional reading, like indicated by this little book icon. So if you follow this link to Probsting's law, you can find a short article written about a law of computing that is essentially a little bit of a joke. In particular, if you've heard of Moore's law, you've probably heard of Moore's law. It's a subject of great cliche and great renown at this moment. And Moore's law says that, roughly speaking, every 18 months or so, the performance of computer hardware roughly doubles. And this, of course, was true during the heyday that ended around 2005 or so, when scaling and transistor density really did translate into performance. Probsting's law is a joke about the significance of compilers research that says the performance of the resulting code performance of optimizing compilers doubles every 18 years. So it's kind of a joke to put in perspective, like what like the relative magnitude of the impacts of the people who work on making transistors small and smaller versus the people who work on making compilers better and better. I think that it was originally given that name by a guy named Todd Probsting as a joke, and like he wasn't actually expecting this to be borne out in reality. But I encourage you to give this paper a read. It's just a short read by someone who like sort of went back and said, well, it was kind of a joke, but is it actually true? And they went through some machines at the time and like went back to earlier versions of compilers, compiling C programs, and observed that actually, yeah, it kind of is true. That is, like, roughly speaking, over time, the performance like does kind of follow an exponential, but a really, really slow exponential compared to the performance that is yielded by more and more transistors turning into better and better CPUs. This is all just sort of a tool to emphasize the fact that language implementation is should not be limited only to compiler optimizations. I believe that compiler optimizations are super important. Compiler optimizations are not just about optimizing ordinary C programs for ordinary CPUs. I think at this moment in particular, there's an explosion of need for new compilers. And the reason for this is that there is a rapid expansion in the number of programming languages that people want to write and the number of different kinds of hardware that people want to target to. That is, about the expansion in programming languages. It's not just about general purpose languages. If you've ever used R, for example, or if you've ever used TensorFlow, these things all sort of count as domain-specific languages for one purpose or another that people actually want to get good performance out of. And it's not just limited to one or two high-profile examples. I believe that domain-specific languages are really proliferating because they're found to be a better way to match the semantics of how people think when they want to express programs to computers. And at the same time, because of the end of Moore's law, the diversity in hardware targets is also in the middle of expanding. You may know, for example, about Google's TPU being deployed in their data centers for running machine learning workloads. But there's also, just in everyone's cell phone, dozens and dozens of specialized hardware units that just do one particular thing very well. We're kind of running into this n times m scaling problem, where the number of programming languages that people want to compile is expanding very rapidly. That's n. And the number of hardware targets that people want to compile to, that's m, is also expanding very rapidly. So either of those two things by itself would mean that we have a great need for new compilers to compile new languages to hardware. But the fact that they are both expanding at the same time means that that's a multiplicative effect. And there's a huge demand for new compilers that do new kinds of optimizations for new kinds of hardware and new kinds of domain-specific semantics. Just as an anecdote, I think it's almost a cliche at this point when you go to computer architecture conferences. I spend half my time as a computer architect. That people are building lots of hardware that they find super interesting and can do one or two things extremely well. Novel hardware is super exciting for individual applications, but nobody knows how to write compilers that unlock the full potential of those domain-specific hardware accelerators. Specialized hardware is not actually something that anyone wants if it's too narrowly targeted. And if people, as is the dominant trend in computer architecture conferences, if grad students have to manually write assembly code for every new accelerator they develop, for every application they want to compile to it. The problem is that we don't know that the science of compilers is not advanced yet. The science of language implementation has not caught up with the massive explosion of domain-specific languages and novel hardware targets. All of this together means that it's an extremely important time to be focusing on compiler research and to focus beyond just the classic but very important notion of just optimizing programs, but to take into account all the other things that we want to get out of a language implementation, including correctness and security and debuggability. All of these things matter. All these things matter, and all of them are surprisingly hard to do. And we're going to need to do them many times over if we're going to capitalize on this explosion of diversity in both languages and hardware targets. That concludes my excitable motivation about why we're studying compilers and language implementation more broadly in 6120. I want to now take you to the syllabus to talk about how this class is going to work. And I have to give the qualifier that in general, I have no idea how this class is going to work. Relative to other semesters, this is a time of incredible uncertainty, and we will just have to see how this goes. I'm going to give you my best guess about how things are going to run for this fall, but I ask you for your patience to bear with me while we figure it out on the fly. On the 6120 website, there is a tab at the top of the syllabus, and we're going to go through a few of the details right now. One thing we've already seen is that we're using this chat tool called Zulip, which is a kind of like weird open source Slack-like thing that has a few cool features that I think will make it exciting to try for 6120. Again, thanks for bearing with me while we try this out. We're going to do all the communication through Zulip, so it's really important that you sign up for it and that you pay attention to it. We're going to do a lot of required discussion participation that happens on Zulip. So you need to familiarize yourself with it and to actually participate when it comes time. There's a bunch of links to Zulip. There's apps for all the platforms you can get, and they are perfectly fine. The iOS one is actually sort of garbage, but that's neither here nor there. And there are also links throughout the webpage that go to individual threads of conversation called topics in Zulip that we'll be using, and you can just use Zulip right from your browser as well. Okay, so let's talk about what is happening in the actual class section. So nominally, this class is 9:55 to 10 something, 9:55 to 11 something rather on Mondays and Wednesdays. But most of the actual stuff that we're doing will be asynchronous. In particular, I want to try out to deal with the complexity of like hybrid in-person virtual scheduling. I'm interested in most of our class sessions being flipped in the sense that you'll be watching videos and reading materials offline, like you're doing right now with this video. And then the actual class sessions, the majority of them will be kind of quiet work times. And you can come and hang out in person, hopefully outside some of the time, and hack and ask questions on Zulip if you are in Ithaca. And if you're remote, then you can join those things by hanging out on Zulip and silently hacking and asking questions and participate just as much as anybody else, because everything will be sort of coordinated around our funky chat system. But in general, these classes will be divided slightly more granularly than that. If you look at the schedule is a tab at the top of the webpage as well. You will see that there are sort of two types of classes. The first one, which is today, is that the class has lesson content in it. And this has a link to a particular lesson that will have a video once it's done being recorded, and there's some notes, and there's some tasks to complete. More on this in a second. But you can, before these classes, do the optional reading associated with them and watch the video. And then when we show up, we'll just be doing sort of silent work time in the flipped classroom style on the tasks associated with the given lesson. On some other days, there will be a discussion to be had. So there's some reading material that is not optional, but is actually required to do ahead of time. The first one will be on Monday. And the difference with these is that we will not have any in-person content. And the reason for this is that we're going to have a discussion, a live discussion on Zoom. So I just cannot even fathom how it would work to have a productive discussion where some people are in person and some people are remote on Zoom. That just seems like totally unworkable to me. So for those days, for the discussion days, those things are going to be all virtual. They're going to be all on Zoom. So please join at the appointed time, synchronously, for a short discussion that the leader for a given paper will be conducting. It's not going to take the entire class time. The rest of it is going to go back to the sort of flipped classroom work time, but we will have a chance to sort of follow up on the discussion that happened asynchronously over Zulip in the days leading up to the class. So just to summarize, when you are participating in this class, it's important that you go to the schedule every so often and look at the upcoming days and see whether they are discussion days, in which case we're going to actually have a discussion, and you have homework to do beforehand. And the homework you have to do beforehand is reading and participating in discussion on Zulip, or they are lesson days, in which case your homework is to watch the videos and to do the optional reading, but the actual work that we'll be doing will be starting in class, so that everyone's working together, can ask each other questions. I hope that makes sense. So the next thing to talk about from the syllabus is the actual work that will go into the class. There are 4 things that you have to do of various shapes and sizes. The first one is smaller implementation tasks that are associated with the lessons. So they're meant to kind of follow up on the things that you'll learn in a video like this. And they're sort of smallish self-contained tasks that are still nonetheless like have some interpretation to them that you complete on a fairly short turnaround. So like most of the deadlines are about a week away for these things. There are tasks associated with this lesson, which I'll get to at the end. They are no big deal, but they are due in a week. The next thing that you have to do that you'll be graded on is reading the research papers and participating in discussion. So participate in the discussion asynchronously on Zulip, and then when it comes time for synchronous discussion, if you're participating synchronously, participate by talking on Zoom. For one paper, I think for the entire semester, you will be leading that discussion. So your job is to read the paper ahead of time and to lead the discussion by doing the following things: writing a blog post, which can come with an optional video if you want, leading the online discussion on Zulip ahead of time. That means coming up with discussion questions and getting people to actually answer them and engage. And then finally, leading the synchronous discussion that happens on Zoom. So you'll do this one time throughout the entire semester. The rest of the time, you're just a participant. Then finally, there is a course project. So at the end, in addition, this is totally separate from the sort of smaller implementation tasks. The course project is a kind of entirely open-ended, kind of do whatever you want that's related to compilers thing. And there's details about that later. Okay, so number one, let's talk a little bit more about these implementation tasks. The tasks for lesson 1 are fairly straightforward. There are 4 of them. They are not complicated. They're just meant to get you familiar with things and to get you to do a couple of like kind of class warm-up things. The first thing you need to do is actually read the syllabus. You're getting some of the information now, but I would really appreciate it if you were to like read all the actual details there. The second is to sign up for Zulip and to introduce yourself. So this links to the introductions topic on Zulip that you can follow it right there and just write a couple of sentences about yourself. You can see my prompt at the top. The next thing you need to do is pick a paper from the class schedule that you will lead the discussion of. So if you follow this to the schedule, you'll see that there are lots of papers that say TK next to them. So for a given day, someone is supposed to be leading this, but we don't know who. If you go to this link, you'll be led to the GitHub repository for this course. I didn't mention before, but this course is entirely open source. Everything is on GitHub that you can possibly imagine. This is the repository on GitHub. This is my username, and this is the repository. And everything that runs the website, which is everything that runs the course, is open source in this repository. So that includes this funky file that lists everything we're going to be doing in every day, on every class day. So, for example, this is a class day where we'll be reading a paper by Lopez et al. About automatically verifying a domain-specific language for specifying people optimizations. It's a really sweet paper, so somebody needs to lead this. Your job is to open a pull request to put your name in right here. That is to claim one paper throughout the entire semester. You can fork this repository. You can use GitHub's in-browser editor thingy to add your name, but please do that as part of the tasks. The last task is to tell me that you did it. And this is true of all tasks associated with lessons. You'll log into CMS and find the appropriate task. This one is the L1 intro tasks. And you just need to basically input a marker to say that you did the thing. So for this thing, there's not really anything to turn in. CMS doesn't let me have nothing to turn in, so you can just submit like an empty text file. There's like a text file submission thing. You just need to like submit something just to say that you've done it. For every other one, I encourage you, I don't require you, but I encourage you to do all your work as open source. So just like the rest of this course, you'll make like a GitHub repository or a Bitbucket repository if you're into that kind of thing, and you will do all your work there. And the thing that you'll submit is just the URL to that repository to say that I have done this thing. You don't need to submit any code there unless you strenuously object to having your work be open source, in which case you can upload your source code instead. But I really do strongly encourage you to do everything open source. This class is really meant to run on the honor system. That is, that like the tasks are meant to deepen your understanding by going through the motions of actually doing something, actually seeing it through all the way to the end, and struggling with the hard problems yourself. as opposed to just looking up the solution that someone else had. So please do everything open source, and please use your own judgment and don't look at other people's implementations unless you totally want to cheat yourself out of the opportunity to struggle with things and figure out yourself, and therefore actually deepen your understanding of the topics in the course. So there's the implementation tasks. One thing I didn't mention is that you're allowed to work in groups if you want to. You can work in groups of 2 to 3 students if you like. You can also work individually, totally up to you. CMS will let you form groups if you want. The next ingredient is this discussion stuff. So as I've said many times before, for the discussion classes, ahead of time you need to read the paper and you need to participate in the Zulip discussion. Where does the Zulip discussion come from? That comes from the discussion leader. For the first discussion, that's going to be me, so you can see how this goes. The things that you need to do include writing a blog post. I have advice here about what exactly needs to go into a blog post that gives sort of your critical reaction to what's going on in the paper. This is not meant to be just a summary. This is meant to be your opinion about what's going on in the paper. You can, if you like, record a video to go along with your blog post. You don't have to do this, but just in case you want to participate in the 2020 style of education, go for it. You will use a pull request to publish your posts to the GitHub repository. That will automatically make it live and go on the internet. I will review it and probably have feedback for you during the pull request process. All of that is, you also need to, once your pull request is open, so even before I've necessarily given you feedback, you have to announce it on Zulip. That is, you have to give people a chance to read your work before it's even ready, and to possibly give you feedback. I will definitely give you feedback, but other people are welcome to as well. All of that stuff is due 1 week before the class that actually has the discussion in it, so that we can have a week of discussion. So as part of your discussion, as part of your blog post, you will have some bulleted questions that you have discussion questions to get things started. And you will post those into the Zulip thread where you announce your pull requests in your brand new blog post, and you'll get people to engage on those questions. Everybody else is required to participate in that discussion. That is, they're required to read the paper and say something, who cares, something in response to it, possibly in response to your discussion questions that you came up with. Then finally, on the actual day of the discussion on Zoom, and again, this is one that does not happen at all in person, it is only on Zoom, you will moderate the discussion on that thing. Don't prepare a presentation. That is, don't go through a bunch of slides. You can have a visual aid if you want, just to sort of organize the discussion. But the point is, you don't need to summarize stuff for people that will already have read it. You just need to be doing the kind of the live version of what you did for your blog post. That is, giving your reaction to it, giving trying to bring a critical lens to the paper that you brought, and to get everyone to participate. It is your job to get everybody to speak up and to participate as equitably as possible. Okay, so those are discussions, both participating in and leaving. So the final thing is a project. I'm not going to go into a lot of details. You can learn about the project online. It's going to be a totally standard course project that is open-ended. You can do whatever you want that is related to compilers. You can build on the implementation tasks you did during the semester, do something totally different, do something connected to your research, whatever. You can see the details here. Deadlines you can find on the schedule as well. There is going to be a blog post at the end of the project. So for all of this stuff, we're going to be using a grading system that we started using last year with the first offering of 6120, which is the Michelin star system. That is, if you do a really excellent job that is astonishing in its breadth and depth, you get a Michelin star. It's meant to recall that even a single Michelin star in the Michelin Guide is a remarkable achievement. So if you do a remarkable job and you turn in something that you're proud of, you get a Michelin star for that assignment. It is possible to earn multiple Michelin stars by being truly exceptional. It's possible to get not a star if your work is merely okay. And that's fine too. You can turn in merely acceptable work from time to time. That's cool. Doesn't who really cares about grades? The Michelin stars will turn into the final course grades. If you consistently get a Michelin star, that means an A. If you consistently miss Michelin stars, then that will slowly reduce the grade that you get. The Michelin star system is meant to get us out of the business of grubbing about individual points and scores, which I think is wholly inappropriate for this open source hacking oriented class that we're going to do for 6120. And instead, meant to focus on what really matters, which is doing a great job and being proud yourself of what you turn in. A final few note on a few policies. So the first thing is that this is a class for PhD students. If you are not a PhD student, it is still possible to take this course, but you need to have special permission to do it. I gave you the directions here. You just send me a short application that answers 2 questions. So undergrads who are suitably motivated can still take this course. There are some policies here about academic integrity. I think that you will find them completely unsurprising. The things that you turn in, that is like the stuff that you represent as your work, has to be actually your work. You are, in this class, it's meant to be open source, and the world is open to you to figure out how to do the stuff. You just have to actually do the work yourself. If any of this enters a gray area, just contact me and we will resolve it. I care deeply about respect within the bounds of this classroom, even though it's, for the most part, not even really a classroom. It is super important that everyone participating in the class, because it's meant to be discussion-oriented, be as respectful of each other as possible. This means being careful about your language, for example. One thing that you should absolutely not do is if you are participating in a discussion and you need to bring up a kind of example person, one thing you should not do is try to make up the gender for that person for no particular reason. That is like to assume that the programmer, the notional programmer for a compiler, is male, for instance. Don't do that. Just don't use a gender for that person. Just use they or them. In general, be respectful of all identities within this class. If you ever notice a problem with respect within the class, please bring it to me, or you can go over my head to the department chair if it doesn't seem like something that I can deal with. There's also a section about special needs and wellness. I want this class to be accessible to everyone. If there are any particular things that this class can do or that I can do to make this class accessible to you, please feel free to let me know. Please also feel free to go through the Student Disability Services office to get an official determination, but I'm also happy just to chat about it. Just send me a message on Zulip. So that's about it. This is the first video I've ever recorded for a class, pre-recorded as part of the course materials. So thanks for bearing with me, I guess. Right now would be an excellent time, if you haven't done it already, to follow this link to the introductions topic on Zulip and to introduce yourself. See you next time. Thanks.